the smaller image as if it has only an individual object, and you won't need the region labeling algorithm. Okay, because then you only would have one object in one image. So if you want, you can do that also, which is simpler by dividing the image, but then you have to be careful when you're putting the objects that they stay in this region, because you can't put them objects sort of over this line, for example. Otherwise that object would be chopped. Whereas if you are treating it as single image and 4 objects, then object could be like this and another one could be like this, and it still would be okay. So if you are careful in placing the objects when you're taking the images, you can avoid, that is, this pixel belongs to what area, and how you make that decision next pixel just by looking at it, because you really can't look at the pixel what the decision is, where it belongs or 8 neighbor connected. This was the pixel, and you are looking at the pixel of interest. So you also look at not only the 4 side pixels, but you also the decision. And the decision is basically then made, so then in that case you would go from 0 to 7, because you are considering 8 pixels. When you look at that, another way of looking at that is in this particular case. So here what you have is the pixel, you are considering pixel P2, P4, P6, P8 around pixel P, and then when you apply the 4 neighbor connectivity to this region, deciding whether this pixel belongs to the boundary and object here which are not touched, that region could be quite large. 4 pixels around it, so this pixel, 4 pixels around it would be this, and this. So this is connected together, so that would be part of the boundary. When you look at this pixel, you would connect, again look at this pixel, this pixel, this pixel, and this pixel, and you would say this pixel is side is matching, so this is part of the boundary. And that's how you would do the trace. And 8 pixels, so even the corner pixel could be considered. And then as well as the 4 corner pixels, and then you would trace, you would get this as an example of the edge, whereas if you look at the 8 connectivity, you would get distribution more looking like that. So what you see, the major difference you see is that there are certain pixels in 4 connectivity are part of the they are seen as part of the boundary, whereas in the 8 connected connectivity, it gives you a little sharper because it takes the corners into consideration, so it gives you a sharper edge of the boundary. So that's why typically people would use the 8 connectivity for following the boundary and identifying which are the boundary pixels. Okay? And all of these pixels would be referred to as boundary pixels. So when you have identified the boundary pixels, then you want to calculate what is like as an example, and we would go next into the calculating of the features from the image. So when you are dealing with the boundary pixel, you have to then count. So like if you are going from, so it would be a diagonal, so you would calculate the value of that. There's a diagonal, so this is referred to as off diagonal connection. So here you go center to center, so this is basically a distance of 2 pixels. You go center of the pixel, you are going 1 and 1, so distance from here to here is 1, here to here is 1, so this diagonal distance becomes then the square root of 2. The square root of 2, so that would be 1.4 or 1.414, say 1.4. Similarly, if this was the diagonal pixel here, that would become 2.8. Okay, because from distance from here to here is again 2 is square, and then square root of 8. Okay, but this pixel, which is on the side, the distance here is not 2 or 2.8. So what the distance here would be is basically, so you are in the 2 pixels in this direction and 1 pixel in this direction. So that's the square root of 5. And I think that's 2.3 or something, I think. Square root of 5, 2.2. The square root of 5, I don't have my calculator with me. So in terms of the distance is the 1.4 times the pixel size. Also, here be 2.8, this would be 2.2, 2.2, this be 2.2, this would be 1.4, 2.8, 2.2, and 2.2. Okay? So basically, when you are doing the tracking using the 8-point or 4-point connectivity, you are looking at the pixels. Is it connected on the corner? Is it connected by the side? And then you would make a decision whether it belongs to the boundary or to the object, or to the object or to the background. Okay. And once you have done that, then you use this parameter, for example. Okay. Is that clear? The distance calculation, that's what was this here. Okay. And count the pixel. If it is connected diagonally, you count 1.4 of them, you will count 1.2 times of the pixel. Okay. And extracting the features from that object, and we calculate the features. Why we need to calculate the centroid? So typically, but there are features which depend on it. So for example, if you want to calculate the radius okay, if you want to calculate that distance, now calculating the distance itself is not very difficult, because once you know the coordinate of your centroid and coordinate here, you can calculate that x minus x1, x2 minus x1 is square, and then plus y2 minus y1 is square. Okay. Similarly, the definition of major axis requires the centroid. So the first thing you have to calculate in image processing is the centroid, and there are a couple of ways you can calculate the centroid. One is this method, where it is basically for all x, the n is the total number of object pixels. So when we are looking at not the total number of the image pixel, because image pixel is like 640 by 480 or 320 by 240. It's not that. Once you have done the segmentation, so how many pixels are in that? That's what the n is referring to. So x, y's, and x's, and then simple process to calculate the centroid, and you can calculate the centroid for any object. So there is no need to, but there is a more efficient method is from the boundary pixels, and that's referred to as the Green's theorem, and coordinates of the kth pixel on the boundary, and n is the total number of boundary pixels. So your summations, rather than going from, so you might have let's say 2000 pixels in the object versus doing for 2000, and the subtraction in computer terms is much simpler operation than the multiplication. That's where you save the cost, the computational time, and the computational cost. That's why the Green's theorem is quite commonly used to calculate the centroid of the object. Okay, so you either one nowadays. I don't think the people are worried about the processing time. It becomes it does become a factor that if you are analyzing a lot of images and you are using that image to make the decision whether you want to use for automation or not. Okay, so either you can use the what I call it is to calculate the centroid, and the centroid calculation is needed for the physical. So typically from the image, the features are textual features, and there are applications where you might have to require the features from. It's not easy to separate where the individual kernel is, because computer is not able to. Okay, so we are going to look at the feature abstraction for these three areas. Another area where the features can be calculated is basically what is referred to as histogram features. So, for example, you could do a histogram plot of not for the right now you're looking only the pixels from the object itself, not the background. So background is already taken care. You have separated that by doing the binarization. You have already identified where the object pixels are. So object now has a very different gray layers. Okay, depending on what you are looking in the object. So you can do a histogram of the object pixels which is basically the density, the density function that different grade levels how many times it occurs. So you can do the plot of the histogram, and you can use the histograms also to for hyperspectral imaging. That's when you're dealing with the histogram features. Any question on so far? Or usually my classes are very active, very interactive. I'm not seeing a lot of interaction.
They are very intelligent people. They are
These object pixels. How do we estimate the area from the object pixel? And take you through how we calculate that minor axis length or thinness ratio or compactness ratio calculated from the perimeter would be considered basic feature. Ratio, on the other hand, radius ratio, mean of the radii would be considered a derived feature because you are calculating all equivalent radius, and if you remember, you go to A, and R would be A by pi on the square root would be a derived. Is the ratio of the basically the area to perimeter to calculate. Is the software? I think the different moments and Fourier descriptors. So these are as you can see, the long list of features. So if you look at, so first one, let's look at the area. To calculate the area, like know what the area of the object is, and that's what basically what you're doing is the counting. The binary image, you would basically put the x, y, z as equal to 1. So you're counting the pixel by basically summing it over the eyes along the rows and the columns of the object, and you would get basically the area of the object. So when you're writing a software, your own software, it's very easy to program to calculate the area. Okay, so you calculate the centroid, next you calculate the area. Then perimeter, as I said, is you basically test diagonally. You count 1.4 times the pixel. If it is then another side test off diagonal, you count 1.2 times the pixel, and then you basically, as you are traveling or rate connectivity, and it would then pixels may fall on the may go to the boundary depending on threshold value, and if you use different threshold value, it may go to the object. So it could slightly affect the area or the perimeter of the object. Now error is not very large unless your image is so poor that it cannot the contrast is not sharp enough to be able to differentiate the object from the background. Then you can have quite significant error because you can have maybe 1 pixel around. The error could be 1 pixel along the whole boundary where your extra pixels are counted or not counted. And if the fuzziness or the image sharpness is not very strong, it could be even 2 pixel wide. So that's why the sharpness of the image is very important, and that's why the uniform, the illumination we talked this morning is very important, because you want to have as contrast as possible, so you are not counting radii determination. So the radius, so there could be, again, depending on how many boundary pixels, so there could be 200 values of the radius. And then from those 200 values of the radii, you calculate find out the maximum radius. Okay, that could be one of the features which was listed. You can calculate the standard deviation of the radii of the boundary pixels. This one is showing you the longest line you can draw through the object, but the connected pixels. Because in this case, for example, if the object was funny shaped like this, and centroid may be here, so you can do the longest distance could be this distance, which is not going through the centroid. Okay, so it has to go through the centroid, and you find the longest distance. So through the centroid line going through the centroid, but the longest distance along the two boundary pixels, between two boundary pixels, and you basically calculate the long through the centroid major axis. But the shortest distance defined is what is referred to as the bounding rectangle. So, and then perpendicular here it would be more like this. In this coming here, So in this case, the bounding rectangle is not going through the centroid in this case. In this case, it is the maximum distance between 2 pixels and when the line goes to the centroid and perpendicular to the line of the pixel. And then from that you can calculate many features. Okay, bounding rectangle we talked about. The moments. Any question on the simple?
Please repeat the bounding. Please repeat the bounding rectangle.
Okay, bounding rectangle. Maybe I would draw a different shape.
Actually, bounding rectangle is like graphic. We can try an object. We can measure the axis.
So let's say the object was more like this, as an example. So you would draw the line tangential to this. Okay. So the length and width of this rectangle becomes when it goes to the centroid, which would be a different line. So the centroid is here, then the maximum distance may be here, which may be shorter than this bounding rectangle. Okay. Yeah. So it's a different way of defining the major axis and minor axis, and both are commonly used in the literature. People just have to make sure they are telling what so the features, so you can use the major axis. That is then this kind of squareness in the object as differentiates the objects. Okay? Yeah.
Sir, computer itself going to perform the calculation for major and minor axis, or we have to perform calculation manually and fed into it?
No, you don't do any afternoon. That's the only time you would calculate these things manually. So to calculate, for example, the bounding rectangle, you basically calculate because it's just going through going through the difference. So you take the boundary pixel of the boundary pixels. Once you do that calculation, because computer can do that calculation, similarly, which is so perpendicular to that line, so you start with then collecting the boundary.
These calculations are done in MATLAB or any particular
software available, but you can
available online.
Some of them are available free online. Yes.
So they don't require to buy the software, or they require to buy.
MATLAB, if they want to use MATLAB, they would buy.
But we have, like in our university, that can be used for the same age.
Even 2 licenses, then two people can use it at a time. So the I think I'm trying to remember 10 years ago, basic, I think Visual Basic, to calculate, say that how you test that your algorithm is working right. Okay, so if you are writing your own right value. Okay, so we will talk about how to test the algorithms. Question? Okay. So the more you do those calculations and get the derived features. Objects. So either you can do the moments calculation just when you are dealing when you calculate the moment, you basically are calculating. It depends how many features you want. Like you can just calculate classification, but increase the calculation time.
So we are basically which are original like parameter, area, major, minor axis. We are derived feature.
No, so same thing. Like of numbers. So you can say, for example, when you're doing the image analysis, you can say, I'm going to make the decision just based on the area. And you can make that decision and only calculate the area and nothing else. Problem with that is the many objects may have the same area. So for example, a kernel of wheat and kernel of barley might have the same area. Okay, but you can't now, but maybe we can go with the perimeter. The same thing, like if you use a single perimeter, so 2 objects can. So some of the features would be independent, which would add much more, but it might add when the objects is of the ratio would help. Okay, so roundness would help, or Faraday diameter. So depends used is that once you write the program, or once you use the contribution of each feature to the classification. So you might run 230 features or 400 features, and you rank them by order, rank them in the order of their contribution to classification. And then you can say limit my classification based on the top 20 features. Okay, then those top 20 features, but you still would have to do some that analysis to identify many features. And there may be another feature which could be much faster.
Teachers, they have to do some principal component analysis or
Many tools they can use for calculating their contribution to classification. Many tools.
multiple regression if you have 4 or 5, but if you have 200, 300,
Yeah.
then you cannot have multiple.
Yeah. Okay. So the journal moments then are calculated. We're okay. So journal moments are, for example, if you want to. So in this case, you can have the PQ can go from 20, 03. So many moments you can calculate as many as you want. So when you're dealing with the whatever value you give, so you can calculate the different moments and the or using the boundary pixels. You can calculate basically using this the x and y coordinates, and their ratios by M00 would give. So these would be the new features you would be adding. Okay, so if you were calculating the moments, depending also, we were talking about the object in the age, y, I, or coordinates are different. So, and that's all you are doing the summation and classification, because if it is dependent on position, different moment value. So the moments are not very good features in the sense for using for the classification, because these are position dependent, but very good for calculating the easier way to calculate to translation. I mean so the center moments are invariant to translation. Neta PQ are invariant to translation, and this or this. You would like to classify all three of those objects as circles. Okay, so the size, it should not be affected by the size. The circle would remain a circle. Invariant to both the location of the object in the image as well as the neta EQ. So first you calculate the mu PQ by using the coordinates. So this centroid values. Once you calculate PQ, you divide by the first, and then the neta PQ are the features you want to use, because these are independent of the translation, size, and orientation. Location in the image, size we talked about, and the orientation of the object. So whether it is located in this direction or in this direction, it shouldn't. So the location in the image, the size, as well as the orientation. Size here are independent of all three, and that's why mean radii or the maximum radius, minimum radius, and other type features you would calculate are the moment invariance. Any questions? Okay. Next, then group are referred to as the Fourier descriptors. Now, Fourier descriptors are used to differentiate objects which are distinct in the boundary shapes. And the Fourier descriptors or moments, we are not as sine and cosine functions. Any sensor or any object can. So typically the Fourier descriptor come in handy when you are dealing with the object. You would use the Fourier descriptor would come in handy. But if you were classifying a bee turtle and I would say rough rice would be a good example, where there are a lot more variations along the edge on the boundary than the wheat kernel would have. Formation of when the boundary is has variations, and it's to define with the distinct boundary shape or of the sine and cosine functions. So depending on lower with a high frequency, so you taking that into consideration, either just using the boundary pixels or using the radius. Okay, and the first order Fourier descriptor gives you the bendingness. The third one captures the triangularness in the boundary conditions, and the F4 the squareness of the objects. Okay, and this is a simple basically method you calculate. Again, as you can see, is the discrete Fourier components can be calculated. You want to use depends, like typically, and most people might use any number, but typically I would say most people would use the first four imaginary parts of the the calculated number. The undulations you have on the boundary, that's how you are capturing that undulated shape of the undulations. If if it was smooth, then RK would be very smooth, like it would not be changing much, so you would not be seeing these variations. So that's how you can basically capture that irregularity along the boundary. Okay, so you can use the boundary pixels. Or any questions on? So we have talked about descriptors. Okay, when you calculate all of these features, why we need so many features?
Use Pascal's to get the boundary.
Zero order moment is the best way to determine, the fastest way to determine the area. The Fourier descriptors are more looking at is these variations. So if there was if your object has a lot more, or like I think an example would be a strawberry head, for example. So if you are trying to detect the like especially when you cut the strawberry and it has the stem end is still attached to it, you see a lot more variation on that, and if you are going to use that information for classification, then Fourier descriptor would be useful. But in wheat, like wheat class identification, you don't need a Fourier descriptor, but when you're comparing wheat and barley, Fourier descriptor, like you can calculate almost in the morphology alone, somewhere between 40 to 60, that you could have the same area and you will not be identify them. So that's where you would start using then the maximum radius and minimum radius might come in handy, because circle would have both the same, and rectangle would have them the longest and short, and square would have somewhere in between. So the maximum radius and the minimum radius might be a feature which might help. So when you do the rank ordering, you might find that those radii are playing the role in project. You don't know what feature would be able to classify that object.
But one question came to my mind, like if we have, for example, 25 features, right?
Yeah.
And there are only 4 fields, then how to combine all these 3 features to distinguish between the remaining?
I'm not getting, so
means I have 100 of, for example, 100 varieties or 100, the wheat varieties, and there is only 3, the features. I want to identify a variety which has only 3 or 4 features which are different from the other. And how you combine all these things?
okay, so basically what you would have to do is in that in the example you're giving, you still would have to calculate the features of all grain kernels.
Yes.
But all the features, and then you would do the, as I was saying, a statistical rank ordering, and what you might find is that if you were identifying those 3 particular varieties, and that became one class, so you can say the varieties which look like this, or varieties which have this kind of surface characteristics would be class 1 or class 2 and class 3. So in that case, you might say that to classify these objects, the features which in that case could be Fourier descriptors might be the one which are playing the role in classifying those 3 classes or 3 different varieties. Then you would use basically Fourier descriptor for all of them to reject those who are not belonging to that class. Okay. So you would have to basically calculate the features, all features for all objects, and then do research, or the person who is familiar with the image process. So your feature calculation process would be the same. It's once you have calculated those features, the classification stage is when you would make a decision which features to use for what application. Okay. Any other questions?
So we have to calculate all the features and then
and once you calculate all the features, then depending on the application, different features may become important. So once you have the software to calculate all the features, now you have to design automation for this part. might require only these 6 features, but automation of second process might require 10 features, but different 10 features. And so once you know which features are the best for that particular application, now you don't have to extract all the features, you only would extract the 10 features. And or you extract 6 features for this application, and this could be very different. But to decide which 6 or which 10 to use, in the initial stage, you would have to calculate all the features and do the statistical rank ordering, and then decide. So it becomes application-specific situation. Okay. How are we doing for the times? This is almost there. And these are some of the examples. Like both of these have same area, like 6400 pixels as an example. So if you were using this area, you would not be able to classify these 2 objects. So I think we will maybe stop here, and then color feature and textual feature we might cover tomorrow. The tutorial by calculus, we would get some graph papers, and depending on how you draw the line and which way it would be. So square the dots